It's in the back. This one?
Yes.
Yeah. Okay, so bullet. Yeah, take the microphone. Okay, so next speaker, Amanda Chavez from Northwestern University, talking about orbital analysis of HR8799.
Thank you. Can everybody hear me okay? Yeah? Okay. Hi, my name is Amanda Chavez. I am a graduate student at Northwestern University working with Jason Wong. And today I wanted to talk to you a little bit about my work on the orbital analysis of HR8799 using high precision astrometry from the gravity instrument. And so this work is done in collaboration with the exogravity team. Okay, so especially amongst this crowd, HR8799 does not really need an introduction, but just to sort of level the playing field and remind everybody this is a multi-planet system with 4 giant planets at separations of 15 to 70 AU. And we all know and love this GIF created by Jason showing the accumulation of data that we have for this system over several years. And I'm also showing the first detection of this system from the early 2000s. And so HR8799 has been studied extensively in the past. And so my work here is acting as sort of the next iteration of this work, constraining the orbital parameters, but using more precise data. So specifically, I'll be referring to the analysis done by Quinn Konopacki in 2016 and also by Jason Wong in 2018. In 2016, they were using NERC2 data from Keck, and this got astrometric precision of around 5 to 10 milliarc seconds. And we can see on this plot on the left that with this level of precision, we're still able to constrain the orbital parameters, specifically for semi-major axis and eccentricity, pretty well. We're seeing pretty circular eccentricities and nicely peaked distributions for semi-major axis. And so when we push to higher precision data with great instruments like GPI and Sphere, we can see how those affect the orbital parameters in this plot here on the right. We can see that the semi-major axis distributions continue to get further constrained, but more importantly, if we look at eccentricity, we see that we're starting to tease out differences in these eccentricity distributions, particularly seeing more eccentric orbits for the inner 2 planets, E and D, shown in yellow and green, and more circular orbits for B and C, the outer planets. So like I said, my work here is sort of the next iteration using gravity data. So gravity is an interferometer, and it gets down to an astrometric precision of about 0.1 milliarc seconds, so at the sub-milliarc second level. Here I'm showing a plot from the first use of gravity on an exoplanet from LaCour 2019. And we see compared to the previous data in the gray color points that for our gravity point in the black, we have to zoom in several hundreds of times before we start to see error bars on our point. And so this can really highly constrain our orbits. And in fact, this plot is for HR8799E, the innermost planet. And so the data set I'm working with makes use of on the order of 15 nights of observations for HR8799. Not all of those observed all 4 planets at the same time, but just for a sort of to get the scale of the data set that I'm working with. And with great data comes great responsibility. Upon doing an initial orbit fit, we saw some non-physical outliers in the astrometry, things that we wouldn't expect for Keplerian orbits. So I sort of went on a deep dive into the gravity data products for these observations. So that's what I'm showing here in the middle panels. Since gravity is an interferometer, we can think of this as sort of the double slit experiment, where these lobes on these chi-squared maps that are in RA and DEC offset space show us the probable positions for our exoplanet. So this is from an observation in 2019 of HR8799E. And ideally, these chi-squared maps would be really nice looking and point us towards one lobe that we can point our data reduction pipeline to and get our astrometry from. But that's not always the case. So what we can do, particularly for HR8799, is make use of all the years of data and sort of align our astrometric reduction with orbit fits that use GPI, Keck, and sphere data. So that's what I'm showing in that top panel. And even further, we can localize our predicted position of HR8799 to the date of this gravity observation. So that's what we're seeing in this red clump of dots in the bottom middle panel. And luckily, they line up nicely with one of the chi-squared lobes. So when we nudge our data reduction pipeline in that direction, we can see that we're able to recover this data point and align it more with neighboring nights of observations. So long story short, this was not the only case of this outlier saving project. We did this for several nights and across all 4 planets. But once we got our data in check in our astrometry, we were able to start getting serious about orbit fitting. So to do the orbit fitting, I'm using Orbitize, which is an open source Python package specifically for the orbit fitting of directly imaged objects. And here on the left, I'm showing what the orbits of HR8799 looked like before we even considered gravity data. So this is making use of, again, Keck, sphere, and GPI. And we can see that we already had a pretty good idea of this orbital architecture. But once we add our gravity data points, and I should note also within Orbitize, it's easy to incorporate the HGCA data that we've been hearing about a little bit earlier. So I went ahead and threw that in there as well to get dynamical masses. And we do a lot better. So we can see that our orbits are more tightly constrained, and I could show you a bunch of corner plots, but I won't put you through that. Our constraint, however, doesn't have to end there. The next thing that we considered are which of these orbits are stable for the lifetime of our system. So HR8799 is around 40 million years old, and we can see which of the subset of these orbits can last that long. To do this, I used rebound. So I'm feeding the orbital parameters from our Orbitize fit. There's around 2 million of our orbit solutions into rebound, reconstructing the architecture and then integrating it forward for 40 million years to see which orbits end in an escape of a planet or an encounter of 2 planets. Those would be considered unstable and wouldn't make it into our final subset. And after testing millions of orbits, we get a pretty nice sample of around 3,000 stable orbits that survive this 40 million year time scale. And so from this stable orbit subset, we can go back and look at how the parameter distributions have changed. So again, referring to the 2016 and 2018 analysis, this is where the stable orbits lie. So we can see in semi-major axis, the distributions are again more constrained, but in eccentricity, we start to see again a separation of the eccentricity of the innermost planet E, which is shown in yellow, tending to be more eccentric than the second planet D. And we can also look at different aspects of our orbital architecture, such as the coplanarity of the system. So here I'm plotting the mutual inclination of each pair of planets moving outwards. So each distribution is a different pair. And to kind of guide your eye, I've drawn the medians here, or plotted the medians here in the dashed lines. And we can see that we're tending towards a few degrees of mutual inclination, but previous analyses of the system have assumed pretty much a coplanar architecture. And so hopefully we can use this new information from the gravity data to analyze the system further. We can also compare to the orientation of the outer debris disk. So here I'm using the solution from Farmaz 2021 for the orientation of the outer debris disk here, and then comparing the mutual inclination to each of the HR8799 planets. And we can see that for the outermost planet, B, here in the orange distribution, we're tending to a mean of almost 10 degrees mutually inclined. Yeah, I think that's all I wanted to say about that. We can also, yeah, I'm running out of time. So we can also start to look at things like the resonances. So here I've just plotted the period ratios for the stable orbits. They're tending towards a 2-to-1, which is what we expect for this system. We've considered it to be in the 1, 2, 4, 8 resonance lock. However, the outer two most planets are tending towards higher period ratios. And going a step further, since we have the rebound simulations that track the orbital parameters across the 40 million year time scale, we can see how the resonant arguments between pairs of planets change over time. So here in collaboration with Nick Choksi, who's here at Caltech, and so graciously made this plot last minute, we can see a subset of 3 of the stable orbits. I'm plotting the two-body resonance arguments, so this is the sine phi over a chunk of 100,000 years. And we can see how this value is changing over time. Long story short, we sort of expect to see this behavior for planets that are in resonance. We expect to see sine phi librating or bouncing between 2 of these values over time. This is very much a work in progress. I haven't gotten a chance to look at the other pairs of planets, resonance angles, but I think that that's something that's really interesting coming up in the future. And I guess the summary is that there's still a lot of interesting stuff, science that we can be doing, looking at the orbits of HR8799, especially with this high precision data set. Thank you.
This is very impressive. So a lot of the earlier dynamical analysis papers on HR8799 included the 1998 HST NICMOS data. Are those astrometry consistent with the orbital constraints you get? Do they add any explanatory power, or is the precision from gravity so good that it just overpowers any added potential, any added benefit from those old data?
In regards to like the astrometry from way back, yeah, I think if I could have shown like a separation plot, but all of the orbits are really constrained by the error bars in gravity data. So we can see that even for like the Keck data set, they're less considered, I guess, in the orbit fit, and we're really like scrunching down on mostly the gravity data. So I'm not sure it would add too much, and yeah, without making it super messy, I guess.
Yeah, really nice talk. I was interested in the point you were making about these outliers that you fixed with gravity, which is really cool. But I was wondering whether you could comment on whether there's a risk of washing out real wobbles from moons or from kind of other sources of scientific astrometry rather than outliers from the instrumentation.
Oh, okay. So, like in changing the astrometry that we get from the...
Like, is there any risk that you might have a real wiggle that you then kind of guide your solution towards the wrong answer because there was actually I'm not sure that there would be a real wiggle of that Yeah,
magnitude.
I know the one you showed was very...
Yeah, but I have considered doing, using Octofitter, I think, allows you to not have to select one of the lobes necessarily in the data things, but I haven't tried. Or maybe some other people have tried and it wasn't really that useful, I guess, in the end. But
Does your astrometry plus rebound simulations give you any further or better constraints on the masses, either from the mutual perturbations or from the orbit stability?
In the stable orbit subset,
Yeah,
after
obviously.
the rebound?
Yeah.
I haven't looked too much at the differences in those constraints, in like the mass. But that would be interesting. And I have the data on my computer, so we
I think
should
it'll be
talk later.
very interesting.